Okay, good afternoon to all. We are starting here the unit number 4 for the operating system, and the unit name is memory management. So, under this unit number 4, that is memory management, we have to discuss about various memory management strategies, various memory management requirements, then the memory partitioning, fixed partitioning, the dynamic partitioning, as well as the multiple partition allocation that we are going to study here. The paging and the segmentation, you might have studied in the previous year in computer organization, that paging. And the final topic of this memory management is the virtual memory. So in the virtual memory, how the virtual memory is implemented, that we are going to see here. So point wise, if we see the point wise topic which we are going to discuss in this particular unit, number 4, that is memory management. So memory management, of course, it is the main memory management, or it is the one can say that it is also called as the physical memory management, or it is also the actual memory management. It is the physical memory, or in other words, we can say that it is nothing but your RAM memory, random access memory, or it is a volatile memory, right? So in sometimes students may get confused in the word that memory means, they think that it is the secondary storage or the hard disk memory management, but no, it is not the secondary storage. Secondary storage is a total entirely different concept, whereas the main memory, and why it is called as the main memory, because the each and every process, each and every program, when it requires its execution, it needs memory. So when I say the my program executes, when I say the process executes, the process must be placed inside the main memory, right? So this memory management issue, memory in the or in our day-to-day life, we are calling it as a RAM memory, or it is nothing but the random access memory, which is the volatile one. Which is the volatile one means when you switch off your PC, the contents in that particular RAM memory, they get vanished, and when you switch on your machine the next time, whatever may be the processes you are running, whatever may be the work you are doing, all that work will run, or that will get a platform in that particular main memory. So it's a very crucial kind of resource. Just like the up till now what we have discussed the entire thing related to our processor. Up till the previous unit, that is process management, the resource which we focused, or resource which we used in that particular process management, is nothing but your CPU or the processor, right? That is the important resource. Now the second resource management, that is nothing but the main memory management, we have to discuss. Means how, though this resource is a crucial one, though this is a very important resource, how our operating system able to manage the main memory resource, right? Which are the different algorithms, which are the different strategies used by an operating system to handle the different memory management issues, right? Because already just with an analogous, or with a similar to the previous one, means there is a single processor or there is a single CPU, and there are n number of multiple number of processes, right? So how this single CPU or the single processor executes multiple number of processes. The same way, there is only a single memory available, or one can say only, for example, 0 to 1 GB of memory is available, but there are n number of processes, and each process requires some space for its complete execution. So how this thing is possible, how this thing is handled by an operating system, that is the issue to be discussed in this particular unit. So the topics included here, the first point we have to see is nothing but the address binding, how the addresses are bind. So different time, at which time the compile time, load time, as well as the execution time address binding, that we have to see here. Then logical versus physical address space. What is the meaning of logical address space, and what exactly is nothing but the physical address space, that also we have discussed. The dynamic loading and the dynamic linking, the very important memory management concepts. What is the meaning of dynamic loading and linking? The swapping is a simple one, and the allocation. How, suppose there are multiple number of processes, P1, P2, P3, P4, P5. So how this allocation of the memory to this particular process to these processes takes place, that can have multiple algorithms. Means you can have single partition allocation, or you can have multiple partition allocation, that we are going to study or discuss here. And the issues arises in case of multiple partition allocation are nothing but your external and the internal fragmentation. So what is the fragmentation? How the internal external like fragmentation they are different, and what are the possible solution for this external as well as the internal fragmentation, that also we are going to see. And the next important memory management concept is nothing but the paging and the segmentation. These are the two very important concepts that is also we are going to discuss. And along after that, the virtual memory and the demand paging. Okay, virtual memory means which is nothing but the auxiliary memory or it is the temporary memory. How this virtual memory is implemented, that we are going to see. And on the last point is nothing but the page replacement. What exactly is the need of page replacement? Why there is a necessity to replace the page, and which are the steps follow to recover from the page fault if the page fault occurs in the system. Which are the steps to taken to avoid the page fault, and which are the different algorithms to follow for the page replacement, that we are going to discuss. So this is a very important topic, memory management. Your fourth unit, as far as your theory point of view it is concerned, in semester as well as your end semester examination, the maximum we can have the questions, they are based on the memory management scheme. And in your practical assignment also, or in your laboratory work also, there are algorithms that you need to implement in C or C++ language for the toward this memory management issue, right? So we'll just go through one by one point. As the result of CPU scheduling, we can improve both utilization of the CPU and the speed of the computer. To realize this increase in performance, we must keep several processes in memory. So for example, so if this is my memory, right? If I can say this is the memory, and always remember that the initial part of the main memory, say for example 0 to 200 MB, 0 to 200 MB, it is allocated to operating system only. This part is reserved. This part is reserved for operating system, and the rest of the part is nothing but for your external processes. And they say for example this is your 1000 MB of memory. 1000 MB means your 1 GB of main memory, or it is called as the RAM memory, random access memory. So this RAM memory, main memory, volatile memory, you can name, you can call it as. Okay, so memory is a large array of words or byte, each of its own address, and the CPU fetches instruction from memory according to value of the program counter. So this instruction cause additional loading to and fetching from memory address. So in a simple word, we can say that if you want to execute any program, you must, or any process, that process, say for example process number P1, it requires 100 MB of space, right? And process number P2, it requires, say for example 150 MB of space, 150 MB of space it requires, right? So to execute any process, and they have their execution time. So for example process P1 require 10 milliseconds for its execution, and P2 requires 15 milliseconds for its execution, and their memory requirement they have given. So what you need to do here, or what operating system need to do here, they have to bring this particular process P1 inside the main memory and P2 inside the main memory to execute that particular process, right? So when we say that, if we recall your process state diagram, you will find that the process, there is the one can say ready state is there. Ready state means what? The processes they are kept in a ready queue. That ready queue, they are ready for their execution, and once they have been selected by the CPU scheduler, they have been assigned to the CPU or to the processor for their execution, right? So meaning is that, so what is the meaning of it? Once they have been assigned to the processor for their execution, they need some space, or they need some, one can say they need some space where they can execute. So that space is nothing but your main memory. That space, one can call it as, this is nothing but your main memory. So when I say that the process, say for example process P1 require 100 MB of 100 MB space, or say for 100 MB of space. So operating system need to put this particular process P1 inside the main memory. So it will occupy 100 MB of space, that is 200 plus 100 means up to 300 memory location. Up to 300 memory location, the process P1 is placed here. and process P2 require 150. So 300 plus 150, that is nothing but 450, and this is nothing but your process P2. This is nothing but your process P2. So like this way, it is nothing but your 450 address location, right? So so from here it is clear that one can say that this each each memory location has certain fixed address location. Each memory location is having its address location. For example, this is nothing but your 0th address location. This is number 1, number 2, number 3. So this is nothing but 200th memory location. This we can call it as the 200th memory location. This is the 300th memory location, 301, 302, 304, like this way, 451, 452. So like this way, so we can say that these are nothing but the memory location there, and or that's why it is called as the array of words or array of bytes. So memory, you can visualize, or you can uh, imagine like that. These are nothing but the memory location, right? From starting from 0 to 1000. So you can assume that these are the location 0 starting from the 0th memory location or the 0th address space to 1000 address space. So if I start from here 0, 1, 2, 3, 4 up to 200, 200, 300, 450, then 451, 452, like this way, 100 memory location I can have for the different process execution. Getting my point or not? So this is nothing but an array of bytes, or one can say it is nothing but it is actual physical memory. It is also called as the physical memory. And why it is called as the physical memory? Because you can see with your own eyes. You can see with your eyes. You can take in hand. You can remove it from your processor. You can check it. What is the size? You can have the 1 GB memory available nowadays. There are 4 GB memory, 8 GB memory available with the laptop, or even your mobile. They are having 2 GB RAM memory available, right? So importance of this RAM memory or the physical memory is that as the number of processes increases, so each process must be placed inside the main memory for their execution. Each process must be bring inside the main memory. So if P1, P2, P3, P4, P3 placed here and P4 is placed here, but what about next processes P5, P6, P7? Right? Because there are like this way dot 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 up to n number of processes are available in the system. Up to n number of processes are available in the system. But now initially only 4 processes I am able to, our operating system is able to put inside the main memory. So how, and without, see, important point, see very carefully, without placing that particular process in the memory, the process cannot be executed. Remember this point in your mind, or you fix it. Until and unless you put the process inside the main memory, the process cannot be executed, right? So if you want to assign the processor, if you in the sense, if operating system want to assign the processor, if the processor is being assigned, say for example P7 process, see here P7 process is there, and if this P7 process is now assigned processor for its execution, but at the same time this particular process must be placed inside the main memory, because for its execution it requires certain platform, or it requires certain space. It cannot execute just like that. Getting my point or not? The P7 process, though the CPU takes the process, but where to execute, or where to perform the operation on that particular process, so that space is nothing but your main memory space, or one can say it is nothing but your physical memory space. Process cannot execute as it is or in the air. You cannot have the air. So you just assign the process, but where to execute? You must provide. You in the sense operating system must provide a platform, or operating system must provide one can say a way where, or it must provide that particular stage where that particular process can execute. And this stage or this platform is nothing but your physical memory. Right? This is the first point. Second point is to be considered here, or important point is that there are, suppose, n number of processes and only 4 processes are there, and the 4 processes, they occupied all the memory available, like this way, like they given in the example, 200 to 1000 MB, say for example 800 MB space, and this 800 MB space is now being occupied by 4 processes, and the rest of all processes which are there in the line or which are there in the queue, they could not get the processor for their execution. So this is the question, this is the big question, and the answer to this particular question is given by your memory management scheme. So that's why, what is the purpose to study this particular unit? This is the purpose, or this is the aim, to study the memory management. Getting my point or not? Yes, we have, say for example, we have. So what is one conclusion of this particular discussion? Conclusion is that yes, we have the scarcity of the resource. Scarcity means we have very less amount of memory available. We can have only 800, for example, 800 MB or 1000 MB of memory available, but we have n number of processes, and they are having their different memory requirement demands. Like P1 is required 100 MB, P2 require 150 MB, P3 required again 100 MB, P4 required 200 MB of memory. Their memory demands or the memory requirement for their complete execution is different. So how operating system accommodate all these processes inside the main memory and how successfully the processes execute, that is the question, and this particular question is answered by your memory management. That's why we have to study thoroughly, or we have to think on this memory management issues, which are the issues arise here in case of memory management. Getting my point or not? Because until and unless you place the process, until and unless you load that process inside the memory, the process cannot be executed. So it is the baseline, or it is the bottom line, is that to execute any process, the process must be assigned the main memory. Until and unless you assign the memory, the process cannot be executed. Getting this point? Okay. So we'll go to the next point. The binding of addresses. So binding of addresses means, as you know, that there are one can say again, I can say that yes, there are different addresses starting from 0 to 1000 memory locations. Say for example 0, then there is a 100, then there is a 200, 300, 400, like this way. This is nothing but array of block. For example, this is your main memory, and you can consider it as an array of block, or it is nothing but the location, memory locations of that main memory. So 0, 1, 200, 101, say for example, and this becomes 110, 111, 112, like this way, and it is nothing but your, say for example, 998 memory location, and after that your 1000 memory location is there, right? So these are the memory locations available. So say for example, if I want to execute a process, if I want to execute an instruction, that instruction must be loaded inside the main memory. Meaning is that that particular instruction, say for example, very simple case, you might have studied in the assembly language programming, the instructions are there, or the process. For simplicity, I will take move, M-O-V, move A comma B. This instruction you might have executed, or you might have used in your assembly language programming, move A comma B. Suppose I want to execute this particular instruction, I need to load this instruction into some memory location. I need to load this particular instruction in some memory location, right? So until and unless this particular instruction is not loaded inside the memory location, the instruction cannot be executed. So I can say that here. So I can suppose if I load this particular instruction at 100th memory location. So I can say in the another way that the memory so instruction move A comma B is executed at 100th memory location. I can tell, yes, I have loaded that particular instruction in the 100th memory location, and this instruction is being executed from the location, memory location number 100. Simple one, right? The same way, suppose I have written a C program. Suppose I have written a C program, A.C. Suppose A.C is the C program, addition of two numbers. So I want to store the number 1. I want to store the number 2. Then I will execute the program, and I will display. In the sense, the program or the process will display the result, right? So this particular process, say for example, this process is now called as A.exe. Now this A.exe process, where to? So what I do here, I first compile the program A.c. I first compile the program to find. So for example, see here step A.c. I compile this particular program, and I will get here which file I get here, A.obj file I got here, right? Then after execution, so then I execute the program, and I will got here A.exe file. Okay, so sorry here, the letters are not clear, but okay. A.c compile here. Okay, so this is nothing but the compilation, and this is nothing but the actual execution of that particular process, right? So when I suppose when I compile the program, means it checks for the syntax error. Then if all the things are correct, if all the syntax and all semantics are correct, then I get here A.obj file. Then I press F9, control F9 to execute that particular program, C program. And when I execute the program, a.exe get created. All of you know this. A.exe file is being created, and a.exe is now in running state. So I can say this is nothing but my process. This process P1 is now running addition of two numbers, and the process asks user enter number one, enter number two, and accordingly the operation takes place. Right. Now come to our memory management scheme. Now come toward the memory management scheme. I want to execute the program. So the bottom line is that until and unless I place this program inside the main memory, see, until and unless I place this program inside the main memory, I cannot execute the program. I, in the sense, always refer it as the operating system. It is the job, or it is the important function or the duty of operating system to place the process inside the main memory for its complete execution, right? So operating system, what OS has to do here, OS has to place this a.exe program inside the main memory. Meaning is that in other words, or in correct technical word, we can refer that there must be binding. There must be binding of addresses with that particular process. Getting my point or not? So here, just like here, for simplicity, that move a comma b I place here into 100 memory locations. What is this? This is nothing but the binding of addresses. This is nothing but actual binding of the addresses. Means this particular instruction is now bind with that particular memory location. Very simple example. You all are in third year IT. So right now there are so many students. They are attending the lecture. Okay. So all of you, you have got your roll number of TIT. Right. So roll number one is one student. Roll number two is another student. Roll number three is another student. Right. So hence after, so as soon as you got your roll number, so whoever will be the subject teacher or the class teacher or any teacher, they will refer your attendance, your all the examination part of you, or your assessment part of you, all the thing, they will be carried out based on your roll number and not the name, right? Say for example, roll number 7, the performance of roll number 7 is very good, his attendance is very good, but whereas roll number 9 is not attending the lecture regularly. So who is the roll number 9? So we will check it from the attendance list, right? So my point is that once you took the admission, you are now bind with that particular roll number. So binding is nothing but, so this is nothing but the binding. So binding is nothing but you are getting unique roll number. Roll number 7 is the unique number. So only one student, he or she has got that particular number. No other student has got the duplicate number. So meaning is that the number is now bind with that particular name of the student. Getting my point or not? So with the help of that particular number, we can refer in future, we can refer that particular student for his attendance, for his performance, for his assessment, examination, anything. We can have the roll number available with us, roll number 5, roll number 7, roll number 3, roll number 31, roll number 2, anything. So that is nothing but called as the binding of the roll number with the name of the student. Same way with our memory management also. So here, what we have to do here, if we want to execute a process, we have to bind. Means operating system binds a particular address location to that particular process. Meaning is that, say 100 is the memory location from where that instruction is being executed. It is now assigned to that particular move a comma b, right? And that particular instruction is executed from the 100th memory location. Okay, so how much time this binding will be there? So binding will be there till its complete execution. So as soon as that particular process get executed successfully, as soon as that particular process complete its execution, then it will be removed. Once its task will be completed from here, it will be removed from the main memory. So once it is removed from the main memory, whatever may be its address location that get free, 100 is the address location that get free, and the next process or the next instruction can occupy the same location once the earlier process is removed from the main memory. Getting my point or not? So what is the duty of operating system? Operating system, the main important role is here. OS has to bind the address location, particular address location with that particular process or the instruction, so that that instruction is being loaded. See the term loaded inside the main memory. Once it is loaded inside the memory, the process will be executed, the instruction will be executed. And after completion of the process execution, after 100% completion of the instruction or a process, that will be removed or that will be deallocated from the main memory. Okay, and the space now become free. The memory space is now becoming free, and this particular free space is now being allocated to the next process, which is currently in a waiting state, waiting to get the main memory for the execution. This is entire scenario how the operating system does this memory management, right? Now again come to our binding concept. We are binding the memory location with that particular instruction, right? Just like your roll number bind with the name of the student. For example, and there are the three different types where operating system bind the address, actual address or the physical address with that particular instruction or with that particular process. So there are the three different types. That is nothing but the compile time binding, load time binding, and the execution time binding. Operating system binds or operating system assigns, in simple word, operating system assigns the memory location to the instruction or the process when the program is in a compilation mode, or if it not done at compilation mode, when the program is in the load mode or when it is actually loaded, or if it not, when the program is actually executed, that time also the operating system can have its memory address binding to that particular instruction. Getting this point or not? So when, say for example, when a.c is currently, you compile this program. So when the program is compiled, immediately at the compile time, operating system gives that yes, your memory location is, say for example, 235. Your memory location is 235. Getting this point? Your memory location is 235, means a.c will place at the memory location 235, and it will be executed from that location. Means compile time binding, it is also called as the early binding. Compile time binding, it is also called as the early binding of the addresses with that particular process or the instruction. So when the process is being compiled, at the compilation time only, it is going to know, or it come to know that what exactly its actual address or the physical address for the execution. The first timing or the compile time binding. Load time binding means what? When a.obj is being created, and when this, and it create the a.exe file, and when you are going to load this particular process inside the main memory, at the loading time only, means compilation time, you compile the program, but the operating system will not assign the address at the compilation time. It will be delayed till the loading time. When actual process is taken, and when it is loaded inside the main memory, at the time of loading itself, the process come to know that yes, this is my, say for example, 235, whatever it may be, it is my actual memory location, of the a.exe file will be loaded at a 235 memory location, and it will be executed from that location, called as the load time address binding. And execution time address binding, it is called as the delayed address binding. Means operating system will never assign addresses at compile time as well as at the execution, as well as at the load time. When the process actually starts its execution, a.c is compiled and then it is loaded inside the main memory. So when it is loaded inside the main memory, then it starts its execution, and at the execution time itself, it comes to know that yes, my address location is so and so. Or when the process starts its execution, at execution time only itself, the operating system assign the memory location or the memory address to that particular process. It is called as the execution time address binding. It is also called as the delayed binding with that particular address location. Okay, so see here, source program. This is compiler or assembler. You compile the program, or you assembler will assemble this particular program. It is called, and at that time you come to know the memory location, exact memory location or the actual memory location. We are referring it as the compile time address binding, right? Then if not done at compile time, the second stage is nothing but the load time. When this object module a.obj is taken and it is loaded, with the help of this loader, there is one system software or the system software, it is called as the loader. And when this loader load that program inside the main memory, it is called as a load. And your operating system tells that yes, now this is your actual physical address. Then this address binding, we can call it as a load time binding. But if it is not done at compile time as well as load time, then it is done at execution time, when the program is actually brought inside the main memory. And at the time of execution, means when operating system starts its execution, at the same time, it will tell that yes, your execution is started from so and so memory location, called as the execution time address binding, right? So this is the way. So just see this compile time address binding. The process resides in the main memory at the compile time. At the compile time only, the process plays inside the main memory. It generates absolute code at compile time binding. that is memory location of the program is known in advance. Memory location of the program is known in advance. So after compiling, if memory location is changed, then it is necessary to recompile. Means once compile and after that the memory location is being changed, then you need to recompile again because the earlier memory location is different, and after compilation the different memory location is there. So that's why the recompilation is necessary. So MS-DOS program, they have the physical address computed at the compile time. So if there are MS-DOS programs, so they have the physical address computed at the compile time itself. The load time address binding, if it is not known at the compile time where the process resides in the memory, then compiler must generate the relocatable code. The compiler generates relocatable code. So relocatable code means that can be relocated in any address location in the main memory. So final binding is delayed until the load time. So right, and if starting address is changed, then only need to relocate user code. So physical address is calculated at the load time, means the binding is delayed up to the loading of the program. And the execution time binding is the sense that process may be moved from one memory segment to another memory segment in execution, then binding must be delayed until the runtime. So it may happen that the process may need to change its memory location during the execution time. Hence, what operating system does here, operating system delay its binding till the execution of that particular process. At the execution time only, the addresses are being assigned to that particular process or the instruction. So this physical address, see here, important, physical address is calculated at the execution time itself. Getting this point. So these are the first key issues, or one can say key components in case of your memory management. That is nothing but the compile time address binding, load time address binding, and the execution time address binding. Right. Now, next point that we have to see here is nothing but your logical versus physical address space. Logical versus physical address space. So, what is the meaning of logical addresses and the physical addresses? So, physical addresses, you know very well. The actual memory address is called as the physical address. So, this is, say for example, this is my main memory or the RAM memory. And actual physical address means whether it is a 0, 1, 2, 3, right? And initial part is always occupied by the operating system. So, initial 100 MB memory is assigned for the operating system. And rest of, say for example, if it is a 500 MB of memory, so initial 100 memory is allocated to operating system, and next this 101, for example, right? Then this is nothing but your 102, right? This is your 103 memory location. So these many memory locations are there, up to 500 memory location. So this 101, the 100, 0, 1, 100, 2, 3, 101, 102, 103, or 500, these are called as the physical addresses or physical address of the main memory, or they are called as the actual addresses. Getting my point? Or they are called as the actual addresses, or they are called as the physical addresses. Remember this point. So, and the logical addresses are nothing but the addresses that are generated by the CPU. Logical addresses means that are generated by the CPU. Means what? So you might have studied so 8085. It is the 8-bit processor, right? Or 8086. It is nothing but the 16-bit processor. Or nowadays you have 32-bit processor or 64-bit processors are available, right? Then the addresses generated by the 8-bit processor is 2 raised to 8. So what is the how much is the addresses generated? 2 raised to 8 is nothing but your 256 addresses, means 0 to 256, 0, 1, 2, 3 up to 255. These are the address range generated by your 8-bit processor. See carefully, this concept you might have studied earlier, but again you have to recall it. 8085 is your 8-bit processor. What is the meaning of 8-bit? 8-bit in the sense it can have 2 raised to 8 address space, means it can generate 0 to 255 number of addresses, total 256 addresses it can generate. 8086 is your 16-bit processor. What is the meaning of this 16-bit? Means it can have maximum 2 raised to 16. That is nothing but your 65536, means 0 to 65535 total number of addresses it can generate. So meaning is that at 0th location I can have instruction 1. At number 1 virtual location or the logical location I can have instruction number 2. Or at virtual location number 2 I can have next instruction here. right? And your 32-bit processor, you can have 2 raised to 32 addresses. And nowadays, all you are having your laptop with 64-bit 64-bit processor as well as 64-bit your operating system. So it is nothing but 2 raised to 64 addresses. So that numbers comes to in some million here, right? So meaning is that what is the meaning? Point of discussion is that the addresses which are generated by your processor, addresses which are generated by your processor, they are called as the logical addresses or they are called as the virtual addresses. They are not real addresses. Which are the real addresses then? These are actually actual addresses, RAM addresses. These are actual addresses or they are the real addresses here. See carefully. But these addresses which are generated by your CPU, they are not real addresses. They are called as the virtual or they are called as the logical addresses. So see, important, this is very important because the next in the next section also we have to discuss about the virtual memory. So this memory 0 to 256 or 0 to 65536, this particular memory is called as the virtual memory or the logical memory. And the name itself, it indicates it is a virtual. Virtual means which is not real, imaginary. It is imaginary. We are saying that yes, my processor is 64-bit processor. So how many addresses? There are huge number of addresses are being generated by 64-bit processor or 32-bit processor, 32-bit operating system, right? So 2 raised to 32 means it is a very huge number. So that much address space is being generated by my 32-bit processor, right? And we can also say that this much amount of memory in the sense it is a virtual memory is available with the help of this particular type of processor, 8-bit processor, 16-bit processor, or 32-bit processor, or even if it is a 64-bit processor. Getting this point? So come to the discussion again. So logical addresses are nothing but these are generated by the CPU, and physical addresses, they are nothing but the address of the main memory. These are nothing but the address of the main memory. So logical address are also referred as the virtual addresses, right? The compile time and the load time address binding method generate same logical and the physical address. They generate the same logical as well as the physical address here. So therefore, logical address equal to physical. If you follow or if operating system follow the binding method, which binding method? Compile time and the load time, then you can say that the logical address is similar to the physical address. Means say for example, logical address, say for example 256 or say for example 250. This is the logical address. The physical address is also 250. Remember this point. This is the logical address and this is the physical address. If I say the 250 is its virtual address or the logical address, the same way the physical address is also 250. But when the operating system is the binding is performed at compile time or the load time. But if the binding is performed at execution time address binding, that it gives different logical and the physical address. Of course, so if it can have 250 is the logical address, but here it may have, say for example 105 is the physical address. It may happen 250 is the logical address, but 105 is its physical address when the address binding is performed at the execution time, right? So next point is that logical address space is called as logical address space is nothing but set of all logical addresses generated by the program, right? And the physical address space is nothing but the sale of all physical addresses generated by that particular. This is nothing but the your physical address space, right? So how to convert or how we are going to map the logical address with the physical address? How we are going to map the logical address into the physical address? So that is with the help of your memory management unit. MMU is useful to map the virtual addresses to the physical addresses. Because why? Because these addresses are generated, MMU or these virtual addresses are generated by the CPU, and you need to map these CPU addresses into your RAM addresses or actual addresses. Getting my point or not? So this is called the memory management unit. And this memory management unit consists of two registers, that is called as the base register. It is also called as the relocation register and the limit register. Base register. So MMU consists of two parts, that is the base and the limit. So from this particular diagram, it will become more clear to you. Base register and limit register are used here. Base register and the limit registers are being used here in this case. So what is the meaning of base register? So it is nothing but the smallest legal physical memory address, and the limit register means is nothing but the content, the size of the range. It is nothing but the size of the range of that particular instruction. CPU, logical address generated is nothing but 346, for example. Logical address generated is 346. And here is your MMU, that is nothing but your memory management unit, consists of your relocatable or base register and the limit register. So base value is nothing but 14,000. So this 14,000 value is added to your logical address. So logical address generated by the CPU is, say for example, 346. So this 346 plus 14,000, the actual physical address we got here is 14,346. So this is nothing but here in this particular memory location. So it starts from 14,000 memory location and ends at 1400 346 memory location. So value of limit is nothing but your 346 is the value of limit register, right? And value of base register is 14,000. So means start from the 14,000 and ends after 346. Add this 346 to 14,000, you will get here 14,356. This is nothing but the instruction is loaded inside the main memory. So what you are doing actually here, you are converting your logical address. See carefully, yeah? You are mapping your logical address to the actual physical address. You are mapping your logical address to the actual physical address here. So this MMU, this is the function or this is the duty of this memory management unit to convert the logical address into the physical address for a particular process or the instruction. So getting this point. So for example, this is the job one or the process one, process two. The base value is, say for example, 30040 is the base register, and the limit value is, say for example, 1209900. This value is being added to this particular base value, and its memory location starts with this 30040 location and ends with this 420940 memory location. Getting this point. So this is the way how the mapping or the logical addresses are actually mapped with the physical addresses inside the memory. So remember the two concept, that is nothing but the base register and the limit register. Limit register is nothing but the size of or the range for that particular instruction or for that particular program, right? Okay, so I think we shall stop here because rest of the thing will complete or we continue in the tomorrow's lecture.